Okay, let's get started. I do not really find a microphone in this room. So if you cannot hear me, maybe just squeeze in a little bit. Talked with IT, so maybe next class they will bring a microphone here. Come to this class. So this is the software vulnerability and security class. And my name is Zeming Zhao. I am an associate professor in the college. So I work on all kinds of cybersecurity problems, especially hacking, system security. So kind of where my passion is. I like to hack, and I also teach students to hack. So if you want to be a hacker, especially a binary hacker, so this is the right class. Some logistics. First of all, I want to record everything here and also post it on YouTube. So the purpose of this is to make your doing the homework, everything a little bit easier because we are doing a lot of hackings in the class, a lot of demos. And you have to do all the demos, the homework. And some of them is not that simple. So you probably need to go back to the video to see what's going on. But sometimes we have technical issues. So if we do not successfully record the class, you can still go back to previous year's video. Every year I try to introduce something new, but most of the content will be the same anyway. Yeah. So our class will be very technical, and that's why I do want every of you to bring your laptop here and also maybe bring a notebook. You need to draw things on papers to try to understand how things work. So we do have a cloud platform for this class, which hosts all the binary hacking challenges. So you do not need to install anything on your laptop. You do not need a virtual machine. You only need a browser. So technically, if you have a Chromebook, you can take this class. So I will show you the platform later and also explain to you how everything works later. We will have so everything will be on my website. We do use Canvas, but that's mainly for you to submit the homework and also submit the 2 exams. We will have 2 exams. They are both CTFs, capture the flag competitions. So it's open book, open internet. But I do not want you guys to use large language models yet, because this class is about manually hacking things. So you can Google, you cannot talk to other people, but you can Google, you cannot use large language models in the exams. We do have a Piazza, it will be the next page actually. We do have a, okay, I'll send to you guys later. So everything will be on this webpage, including recordings, lecture notes, homework, reading materials I gave to you. But you need to submit your homework from Canvas. So each homework will just be a Word document. Then you will do the hacking. You will show me the evidence that you captured the flag. Then you upload the Word document or PDF to Canvas. That's it for homework. And this class is a little bit late. It's 6 p.m. to 9:20, I believe. So if you guys want to eat, want to drink, I don't mind. And also feel free to interrupt me anytime if you have questions. Okay. Teaching assistant, Jun. He is my PhD student. He's very good. He will host office hours on Mondays, 1 p.m. to 2 p.m. And we have a link on the website. So you can either schedule an in-person meeting with him or you can just ping him and schedule online one. I also host office hour before the class, and also the link is also on the website. But usually I'm available whenever you need. So if you ping me on Piazza to say you want to meet, usually I will be available. Yeah. A little bit about myself. I direct the cybersecurity at the forensics lab. I call it Cacti Lab. I stayed in Phoenix, Arizona for many years. That's why I like cactors. So we do all kinds of research in cybersecurity, from application layers to low-end hardware security, or at least the instruction set level. We do a little bit of hardware security like FPGA and also glitching. To me, those are a little bit hardware, but not necessarily what ECE people are doing at a device level. So we do need all kinds of help in terms of research. So if you guys are interested in doing research, we have all kinds of predictions in our lab. So most of those predictions are related to what we teach in this class. If you really enjoy this class, then usually you will be the guy I'm looking for research. Even some of you probably will be a PhD student in the future working with me. So I had many students who coming out of this class then eventually become my PhD student and work with me. Yeah. So this is the link for our lab. I post all the class recordings here. So this is what you were looking for. Even in the exams, everything I say, the CTFs, I say many students go back to the videos, try to say how to hack. What we do for research, we mainly work on systems and the software security on all kinds of platforms. This class, we will use x86, 32-bit, and also 64-bit. We use both. But our research extends beyond the x86. We also work on ARM. For example, all your phones, some of you are using Mac, and Mac are using ARM CPUs. Today, we will also talk a little bit about ARM CPU, how they are different from Intel CPU. We also work on RISC-V. Cortex-M is a different kind of ARM CPU, mainly for IoT devices. We also work a little bit on FPGA, and also we want to work on GPU or TPU, some machine learning processors as well. We also work a little bit on security in machine learning or security for machine learning or for large language models. I used to work on many other stuff as well, like autonomous driving, picture password, hacking password, formal verification, and also hacking itself, capture the flag computations itself. But right now, we mainly work on system and software security. So if you are interested in this, especially after taking this class, please contact me if you want to do some research. So this is a cross-listing class. So how many of you are undergraduates here? 1, 2, only 2? Okay. So then I say maybe 1 or 2 PhD students, right? Then the rest of you are master students, I assume. So you are regular computer science, computer security program. Any of you from Align program as well? Okay, Align, several Align. Okay. So we also had some Align students who were very successful in this class because most Align students, even though you guys were not from computer science background, but you were very good in your whatever discipline before. Okay, so this is a Piazza link. So if you have any questions, post there or just shoot me an email. All of this class is obviously all about hacking and all about hacking binaries. Software security or software vulnerability is a big topic. There are all kinds of software. JavaScript is software. What you write in Java, what you write in C is also software. Right? So in this class, we focus on binary. So usually those you developed in C or assembly, the machine code level. Okay. So I'm not sure if we have a web security class because web security deserves a class. I think we probably have one, right? So in my class, I don't really cover web security because I believe it deserves another class because the browser itself is kind of like an operating system. On top of browser, you can run all kinds of applications. The browser itself can have many different processes. It's very complicated. Right? So this class is all about the theories, principles, techniques, and also tools for binary software hacking and also hardening. We're not only talking about hacking, we're also talking about the state of techniques to defeat your attacks. And what are the limitations of the state-of-art defenses as well? So we mainly use x86, like I said, 32-bit version and the 64-bit version. We use both because the hacking on them actually are quite different. There are some examples where they are much different. So you will study in depth binary reverse engineering. You are going to use some simple tools come with the operating system like objdump, and you can also use some more advanced tools like NSA have an open source tool called Hydra. Arizona State has a tool called Anger. IDA Pro is the best commercial tool out there. Then you can also use Binary Ninja, which has a free version. So you're going to use those tools to find the vulnerabilities in machine code, in binary software. Then you will write exploits that exploit those software. So as an attacker, you can gain the control of the computer. Okay. So I will show you what it means later when we talk about attack. This in this class is to get your hands dirty. Okay. We have hundreds of challenges I developed all over the years for you. So some of the challenges we do not really cover in the class, but you are free to play with them as well. Right? Get your hands dirty to actually capture the flags. So this class is not really about just understand the principles behind the vulnerabilities. It's more importantly you actually exploit the vulnerabilities, right? So the only way to learn in this class is just to do it. Okay, there is no other shortcut. The homework, exam, or open book, you can refer to the lecture notes. You can Google. You can go back to the videos. So I believe this is more like the actual environment when you are you're doing any work or you are a hacker, right? You have all the resources available for you. I believe this can prepare you for a future real work environment or even scientific research. So I emphasize this class is about problem solving. It's not about memorizing concepts. So where is this class at? I would say several of you took my computer system class last semester, where we talk about operating systems and also keep those general concepts. So with the background, you are well equipped to take this class because we are going to use a lot of knowledge in that class. But I'm trying to make all classes self-contained. So even if you come from a different background, you are a line student, so still trying to cover all the backgrounds, especially today, trying to cover all the background. So system programming, operating system, compiler courses will definitely be very helpful, but they're not necessary. Then after this class, I believe you guys can take advanced software security, which is also a class I offer, but I do not offer that very often. So this class is all about manually finding vulnerabilities, writing exploits byte by byte. Okay? You can use some tools to help you, but still you're writing exploits byte by byte to hack those systems. Then in the advanced software security class, we talk about topics more like how to automatically discover and exploit vulnerabilities using more advanced techniques, symbolic execution, even using AI, right? But I believe you still need to do this manually to understand everything before we move on to using more advanced tools or develop more advanced tools. So this week, we were just to go through the class overview, logistics, then we talk about the background knowledge you need. So you probably have picked up several pieces of background knowledge from previous classes, but please bear with me when we talk about background knowledge because not every one of you knows them. Let's say today we will talk about compiler, linkers, loaders, how they work. We talk about the x86, 32-bit, 64-bit architecture, the instruction set, and also some Linux or Unix fundamentals like the file permissions, what are set UID programs, so how we designed our hacking platform, because that's very related to set UID programs, the memory map of a Linux process, what are system calls. So some of you took the computer system course, you learned system course, but you were using system course, especially you were using C wrappers of system calls, right? So in this class, you are going to write assembly code to directly make system calls using special instructions. Environment variables, share variables, that will also be very useful for our hacking semester. And also some basic reverse engineering techniques. So the real prerequisite for the class, I think it's the C programming language. If you never programmed in C, it will be a little bit challenging for you to take the class. And I cannot cover C programming in this class, obviously, right? So I also recommend you to read this book, the classic, the C programming language book, throughout the semester. Actually, by reading this book, you will find that the classic examples in this book have the bugs we can exploit. Yeah, and we're going to learn how to exploit that. System programming, operating system, computer systems, they all help, but not necessary. The skills you will need or you will learn in this class, reverse engineering. We mainly use obj dump because this tool is so simple. This is just a command line tool, very easy to use, comes with binary utilities. Then there are advanced tools, IDAPro. I'm not sure if IDAPro still has a free version. Maybe there is. Then Hydra is another tool you can try. It's developed in Java. It's a reverse engineering tool. Then another one is binary Ninja. They have a web version. For sure, it's free. Then you can use that. For debugging, we will just use GDB. Okay. So command line based GDB for debugging. We tried to install some GDB plugins on our server, but it was not very successful. So for the Mopang GDB, I do have that on my local computer, but we do not really have that on the cloud environment. So I would say the most important skill for you to survive this class is the same skill you use for any research or real-world jobs. Basically, you need to be good at looking for information, right? Google a lot, or now you just use ChatGPT, but do not use ChatGPT to directly solve the problem, to ask it to generate exploits. Actually, 2-3 years ago, when ChatGPT came out, I was interested in finding out if ChatGPT can solve the challenges in this class. So I had a PhD student work on that for some time. But 2-3 years ago, it can solve some challenges, not all of them. I believe now ChatGPT can solve most of the challenges in this class. That's why I do not want you to use it. Right? I want you to get your hands dirty and really learn. Okay, so what topics we will cover in this class? Battery hacking, 32-bit and 64-bit x86 system as example. You will learn how to discover different kinds of vulnerabilities, then exploit them. Most of the vulnerabilities we talk about here are memory corruption attacks, memory corruption vulnerabilities. Imagine your computer. The most important two parts of a computer, obviously, is the CPU and the memory. Without those two parts, your computer cannot run. The computer here means your laptop, your tablet, our server, everything, right? So those are the two most important components. So the memory corruption vulnerability, memory corruption attack basically means some content on the memory is tampered by attackers somehow. And there are many different ways to tamper them. We will start with stack-based buffer overflow. This is a classic problem. I believe everyone heard about stack overflow. I'm not talking about the website, the attack, stack overflow. Then we talk about all kinds of defenses against this attack and why they work or why they not work. Then there will be a share code workshop. You are going to write some share code. So after you find the vulnerability, you will try to gain control or fully control of a computer or even a remote computer. So which means you need to inject some code to that computer so that computer executes, then give you the control. And that code usually we call it share code. It's used to give you a share, but obviously you can do many other things as well. So in our class, on our platform, your share code do not need to give you a share. It's only need to capture the flag. There is a flag on the platform which has a random secret. You need to extract that. By extracting that, you show us you actually exploit the vulnerability. We talk about format string vulnerability, and we will talk about heap-based attacks as well. So for the last 20 years, there have been a lot of development in defeating all kinds of attacks. So buffer overflow, share code, they are not as effective as before. So most recently, a lot of attacks are heap-based. And the heap is not only in userland, it's also the kernel also uses its own heap. So you can use very complicated method to attack the kernel heap and gain control of the whole system as well. We will talk about other ones as well, like integer overflow, return-oriented programming. This is a fun one. Also risk conditions. If we have time, we will also talk a little bit lower than the software layer. We will go to the cache layer, more like a micro-architecture layer. We will attacks there, depending on if we have time at the end of the semester. So there are several papers I built this class around. For example, Eternal War in Memory, which is a systemization of knowledge paper published 12 years ago, 13 years ago. You can see the title, Eternal War in Memory, right? So it's talking about memory corruption attacks. That summarizes a lot of attacks and defenses we covered in this class. There was another one talking about mainly the attack techniques. It's called the State of the Art of War, Offensive Techniques in Binary Analysis, published 3 years later after the first one. So that one mainly talk about attack techniques, not defense ones. Then there are other related ones, for example, shadow stack. Shadow stack is one way to defeat buffer overflow. And they talks about why shadow stack works, what are their limitations. Also, I will recommend this book to you guys, Practical Battery Analysis. But what we are doing in this class is still a little bit lower layer than what this book covers. This book mainly covers how to use tools to do those. Right? But in this class, I teach you to write, exploit, find the vulnerabilities by hand. So this is a figure I copied from that SOK paper. It summarizes a lot of attacks and defenses we cover in this class. So throughout the semester, we will revisit this picture multiple times. Then you can understand what we have learned, where they are in terms of in this big picture. Right? Okay, so the hacking environment. We have this hacking environment. This is a URL. I will give you 30 seconds there to log in and maybe register your account there. So to access this, you have to be on local system campus, or you need to VPN into local system campus. We wanted to bring this to public, but right now we do not have fundings to do that. We cannot support thousands or 10,000s of students online right now. Yeah. We have hundreds of challenges here, you can see, in different categories. And every year, I develop challenges for the midterm and final. That's why you cannot find them anywhere online. So we have share coding challenges for the background knowledge, heap, return-oriented programming, format string, buffer overflow, reverse engineering, and also cancer attacks. So add the new challenges throughout the semester. So just register an account there. You don't have to use your Northeastern email username, but please do use your Northeastern email address so we can identify you. For each, you need to put your user ID there. Otherwise, we don't know who you are.
Can you also afterwards just put instructions to how to get the VPN if you're off campus? Because I don't have it.
Just to Google Northeastern VPN. What system you are using?
Mac.
Mac. Okay, that's easy. If you guys are using Linux, it's a little bit challenging. Anyone here using Linux? No. Okay, good. So I think Northeastern have very good support for Mac and Windows VPN. Yeah. Linux, you need to go to another open source project to do that. Yeah. Cool. So we do have a much more fancy environment, and we have been developing that for a long time. And we actually need some help because it's a ton of work to develop a new platform and also new challenges. So after this class, if you're interested in contributing, please let me know. So we want to extend from x86 to ARM to RISC-V to other IoT platform as well. So the challenges will also be different. Later you will understand why the challenges will be. So hacking environment, like I said, x86, 32-bit, 64-bit. The principles you learn, technically, they apply to different architectures. But in this class, we only use Intel. We use Linux. Our server uses Linux. The tools, Palm Tools is also a tool I want to use this semester. So you will be writing a little bit Python script. It will not be that difficult because even without Palm Tools, you will be able to hack those challenges by just putting byte after byte there by yourself. With Palm Tools, things can get a little bit easier. So every week, there will be homework. There will be some reading materials, could be book chapters, white papers, papers, or even blogs. Then there are some hands-on exercises. Usually I demo those in class, but you still need to do this as a homework. So you need to submit the homework before each class. So the first homework is due before next week's class, because we need to, sometimes we discuss the homework. So 30% penalty if you submit within 10 minutes after class starts, 0 points after 10 minutes. Okay. And obviously, plagiarism is serious. So we have a big class, and this class is a lot of fun, right? Everything is open book. So you guys are encouraged to discuss, but do not copy others' exploits. You need to understand why the exploits work. If you have a DAS request, please send it to me as soon as possible. For the homework, for each hacking challenge, you need to submit your exploit. Then also a very simple write-up to explain why your exploit works, and also screenshots to show that you actually capture the flag. You also need to submit the flag on our platform, okay? especially for midterm and final, you need to submit the flags on the system because we use that to determine when, because we have first blood bonus for the top three, the first three students who hacked a challenge to get a bonus, and we use a timestamp on the server to determine that. For the simple write-up, you need to describe how you solve the challenge. If you worked with someone else, you need to explain that. Discussion is still encouraged, but do not directly share your code or exploit. And also, please do not post them online. Then we have two exams, midterm and final. They are both capture the flag competitions, open book, open internet. It will be just in class, so 3 hours, 20 minutes. And we will have 4 challenges for each of them, only 4 challenges. You have 3 hours to solve 4 challenges. Great. We have 14 or 15 weeks, I believe, but we will have 14 homework. Each homework 45 points, then 2 CTFs, 360 points, attendance 10 points. We will have anonymous course evaluation bonus. If 19% of you submit evaluation, then all of you, because I don't know who submitted the evaluation, then all of you will get a bonus. We do have some, like I said, first blood bonus for those 2 exams. So the total score actually is a little bit higher than 1,024. So for undergraduates, this column is for undergraduates. This column is for graduates. Slightly different. Academic integrity. I guess you guys are all very familiar with this because you're not freshmen and some of you are master students. But still, I still encourage you to read the law system academic integrity policy. Okay, I'm not going to repeat it here. ChatGPT, large language model policy, like I said, you can use them for homework. You can use them for learning, but you cannot use them in the exams or CTFs to directly generate exploits. Okay. What you are learning from this class could be dangerous, right? You could be breaking other systems using those techniques. So do not break the law. There actually are legit ways for you to use what you learn in this class. There are a lot of bug hunting programs out there. If you find a bug, if you can show that how you can exploit that bug, you submit to them, they will pay you. Google has one, Linux community has one, all the big companies, they have that. So if you find bugs, do not try to bring their system down. Instead, responsibly disclose those bugs to them. They will actually pay you. So that is what we have for logistics. Any questions? Okay, good. Then we can jump to knowledge. So hopefully we can finish all the background knowledge today. Okay, so the first one, we will talk about compiler, linker, and also loaders. So this is a process to convert a C program to a binary program. A C program is just a text, human readable text. It has its own syntax, but it's still human readable. Machine cannot directly run that. CPU cannot directly run C programs. You have to eventually convert that C program into what a CPU can understand, what that's called instructions. And each CPU has its own set of instructions. ARM have their own set, Intel have their own set. So the process of converting that C or many other languages to binary to machine code is called compiling, right? So we have a compiler class to teach you how to do that, which is a very complicated process. So here, let's say we have a .C program, and each .C program eventually will be compiled into a .O program. So all our compilers, GCC, LLVM, those are the very popular compilers we use nowadays. They will do that. So a C program will have some definitions, includes. Right? You can include a lot of file in your C file. You can include a header file, or even a header file can include other header files. So the include is not really, that's a C keyword, right? So the compiler at the very first stage, at the pre-processing stage, will expand those definitions, those includes, into text. Result of that step is something called a .I file. That is still C program. But usually compilers will not save this file in the file system. So you don't necessarily say that. When you compile, you do GCC something, you usually get directly from .C to .O or even to the binary. You do not necessarily get the middle intermediate files like .I or .S. So the .I file is still text file, it's still save file. Okay? So that will go through the real compilation stage to compile that into assembly code. And this is still text. Assembly code is still text. It's not machine code. Okay? Then we have assembly, another tool, which usually Linux will use AS. This is a tool, a part of GCC, or even existed before GCC. That tool will convert the assembly code to binary code. And the binary code or relocatable object files, so they are binary code. They consist of the metadata information. They consist instructions, but they are not text anymore. They do not have the C source code there anymore. You may have multiple C files. Each of those C files will be compiled into a .O file, object file. Then the linker needs to link them together so they become one executable. Okay? So the executable is basically a special type of object file. So it still consists of instructions, metadata, all kinds of metadata. So in Linux, we usually use the ELF format for this executable and also for .O files. After you do all this, you get a file, you get a executable, a program, but it is not really running. So then in your terminal, telling the operating system or you're telling the shell that you want to run this program, right? Then the shell will eventually tell the operating system to load the program into the memory. Only in the memory, the program can execute, the CPU can access that. So that part is the OS or loader. It's a process. So that is the basic step of how a C program or C file become a process. And during that process, we generate all kinds of metadata, like symbol tables. So at which memory address we have a variable and what's the name of that variable. Okay? So CPU doesn't really need that information to run. Information will be very useful if you want to debug, find the problems of program, but CPU doesn't really need that. For CPU, it's just address and instructions. We have many other files as well. So when you run an executable, that executable may call functions from other libraries, which is not part of the executable. Right? So this is very normal. Imagine all your C programs, they will use a library called the C library, the C standard library, libc. If each program will load the same copy of C library into memory, then we're duplicating the C library in memory. That's obviously not a very smart way to do this. So we only need to the operating system will only load one copy of C library into the physical memory. Then all the programs can share that library. So this is a very simple example of a shell. Some of you took my computing system class, then you developed a relatively complicated shell in that class because you have to do several levels of piping, right? Complicated. So here's a very simple one. So a shell is where you type some commands. So most of the commands you are typing, they're not really commands. They are just a program. Right? So some of them are really commands. For example, you type cd, change directory. There is no program called cd. That is actually a command that your shell understands, change directory. When you type a program's name on the shell, so what is the shell? So shell is a program. It takes your input from the terminal, the type of program's name, to create a new program for you. So in a nutshell, what the shell does is the shell will first fork itself. So use the fork system call like this. So here actually this is a function call, not a system call, but eventually that fork, the function call calls to C library eventually become a system call. The fork here actually in modern operating systems will eventually becomes a clone system call, not the fork system call. But anyway, then after this line, we will have two processes. One is a shell, another one is the same as a shell. Okay. Then the fork function will return a process ID. If it is a parent, it is the shell, then the process ID will not be 0. It will be the ID of the child. That's it. So this piece of code will use this PID, the return value of fork, to decide whether I am the child or I'm the parent process. Okay. In the child process, it will just execute the new program, use the exe system call to execute a new program. In this case, like ls. Right? So otherwise, then this is just the parent. It will continue doing whatever it wants to do. So this is basically how a shell works in a very, very simple form. Then think about this. When you develop a shell, you are actually loading a program, a binary program, from the persistent storage to the memory and run it. Even though you are only making this simple system call here, exe a lot of things happened under the hood here, in the loader, in the OS, right? So what is happening here? So first, the OS will validate the permissions, whether you or the shell you have the permission to create this new program. Run this new program. If you have the permission, the shell has the permission, the operating system will set up address space for the new process, which means the virtual address space. Then it will actually load the programs from the persistent storage, hard drive, SSD, flash, whatever, load that into memory. Right? Then the operating system will also check whether this program will need some libraries. Usually we will need libc, the C library. Then you will also load the C libraries there. It may use other dynamic libraries as well. We will decide if we want to load them. So the loader, sometimes in Linux, is also called the interpreter. And usually we use this loader. So this SO means static object file. So this is basically a library file. And the loader or interpreter is stored in this file. Then the interpreter will will set up the virtual address space, memory map, the libraries, relocate some binary sections, and also copy the command line arguments onto the stack. So when you type something in the terminal, when you do ls, let's say we just go to any of our examples. So here we can do ls, we can do ls al, right? So the command here, or the program you are trying to execute is ls, but you are also giving the program a command line argument for the second example, the -al, the -al. We're giving command line options to the program. So how does that program know you gave that option? Some program has to copy that string -al to the ALS program's address space. Okay. And that is done by the interpreter. So the interpreter will copy those command line arguments onto the stack. It will also initialize all the registers, especially the stack pointers, instruction pointers. Then if it's a C program, usually an F program, it will jump to the program's entry point. The entry point usually is _start. Okay, that is just an address in an L file, _start. From there, it will call C library. The C library eventually have a function called maybe _libc start main, which eventually calls your function. So what is your function? If you are a C developer, what is your main? What is the entry point for your function, or what do you develop? Right? Okay. So main function is not the first function that is executed. Before that, there has been many functions eventually lead to the execution of your main function. So it's a very complicated process. So let's see one simple example here. We have, this is a simple project with 3 files, 2.c file, 1.h file. So eventually, how many .o files we are going to get after we compile this? We compile, yeah, we get 2 .o files. Each .c file will get into a .o file. The .h file will not be. It will be inserted into those files actually. So let's look at the main .c file. The first line is comment. So the pre-processing of the compiler will know that that's comment. So it will simply delete that. It means nothing to the compiler. Then it has pun include. So that is a directive to include this file and .h there. Then we include some library files, stdio, string, stdlib. Then we also have a definition here. Then we have a main function. The main function has a standard prototype. So usually it's always like this, a prototype. It has a return value, which is an integer. It takes 2 arguments. Actually, it can take 3 arguments as well. So the version we usually use takes 2 arguments. The first argument is how many command line arguments are there? How many, which means it's an integer, right? So it's int, and we call it argc, argument count, right? So number of arguments we are giving to this program. Then for what are the arguments? Because they are command line arguments, they're basically strings. So we have an array of strings. So here, this one shows it's an array, and the type is char start, which means that's a string. That's an address to a string. Then actually, the more complicated version, you can have environment variables at the end as well. So there are three arguments. Then we have 2 local variables, a and b. Both of them are initialized to 0. Then we check how many command line arguments are there. If the line arguments are not 3, we just print out usage. This is a macro, which is basically a string. Add 2 integers with 50, and it shows how you use this. Right? Then it returns. So if the argument is not 3, it will return. It will not keep executing. Otherwise, if the arguments are 3, we are going to convert the first argument and the second argument. The argument starts with the zeros, right? Convert them from ASCII to integer. Then we just add them together. We just printf. This is a C library function. Then the C library function takes 4 arguments here. The first argument is a string. We call it a format string. Then we have 3 more arguments, A, B, and also we call function add here. And function add is defined here. It has it takes 2 arguments, add them together, and also add 50. That's it. So let's see how we hire this one. We are going to look at the 32-bit version and also 64-bit version of this. So for each challenge, you just need to look for the challenge. So this one is called add. 32-bit. You click it, then you click this button to run this challenge. So what happens is our server will create a Docker for you. So each of you, when you click this, we create a separate Docker for you. So you will not be interfering with each other. After this, you close that dialog, then you just click terminal here. It brings you to that Docker. Okay. So that's why this is totally browser-based. You do not need to install anything here. Okay. We have this program here already compiled. Let's try to run this. Oops. The demo is not going to work today. The IT guys messed it up. What happens is the IT guys did something, so we're using a different version of libc server. But let me try to recompile it here in our. Permission denied. Just to temp. Save. Okay, version. Oh, music language. No, permission denied. One. It works here. Good. So, first. Okay. So I move it to the temp directory. Usually you have permission, anyone have permission to write anything there. Oh. Yes. So here we have the add.c file, main.c file. Then we're going to use the command to compile this. So this make it bigger. This is a GCC command. We're trying to compile those 2 .c files, and the output will be this program called add underscore 32. The optimization level, we use optimization level 2. We are going to compare to a 32-bit program. That's why M32. And we are going to use this option here. That's a key of this. It's called save temps. Basically, we are saving the temp files. So after we compile this, we do this again, and you can say have the .i file, .s file. Okay. If you directly use GCC to compile, GCC will not save the .i file or .s file to the file system. Then we already know what is add, right? So let's say what is add.c. So this is our source code. Very simple. Include, define, for function. Next, let's check the .i file. If we look at the .i file, what do you say? We do not have that include anymore. Okay? We do not have that macro define anymore. Okay? That include becomes this line. Int, int. Basically, the declaration of this int function, which was in that add.h file. The macro doesn't exist anymore. However, here we have base. The macro, now we have 50 instead of base. Okay. So this step is pre-processing. After that, we get the C file. Then, if we look at the .s file, then this is compiled into assembly from that .i file. We have many instructions here. This is AT&T syntax. In this class, we actually use Intel syntax. Then after that, we got the .o file. We can also do a cat for that. Right? If we do a cat for this, you can say we do not really get much information. Right? We do get some strings. Okay? So those are strings embedded in the object file. However, there are many other random bytes cannot be displayed. That's why you do not really say anything here. But if we use OB, we use object dump command to analyze this .o file. The .text section, which is the code section, and we can see the function here. So this is basically the add function. Actually, the instructions. The instructions are the first instruction, NBR32, is 4 bytes, F3, OF, 0F, 1E, FB. Those 4 bytes are this instruction. The second instruction, move something to X, another 4 bytes, another add 4 bytes, another add 4 bytes. The eventually return is C3. So here, .o file is not human readable text anymore, but machine code. We can do the same thing at the eventual executable. In the executable, we will have more functions. We will have that add function because it's from add.c. We will also have functions from main.c. We'll also have functions from the C library itself. Anyone remember what is a start? Where is the start? What's the name of that? It's underscore start, actually, right? So it's actually here. So this is the entry point of the whole program, underscore start. And this one will eventually call a function called underscore libc underscore start main. And this function eventually will call your main function, which is, where's our main function? This one. This is our main function. And our main function calls what function? Remember? It's called printf. It calls add. What else? A to O, right? ASCII to integer, those functions. Then let's see if we can find them. So here, printf becomes puts. So that's also a C library function. A to O actually becomes this string, this operation, and this is our AND function. So the main function will call those functions. So, and those are the instructions. We can do the same thing for the 64-bit. Let's quickly do that. So you can, then we need to copy that, right? No, I leave that to you guys for the homework. Okay, because we have so much to cover. Then we're going to talk about the x86 architecture here. Data types. 1 byte is 8 bits. 16 bits, we call it a word. Double word is 32 bits. Word is 64 bits. Double word is 128 bits. Okay. Endianness. Most of our machines right now use something we call little endian, which means significant byte is stored at the lowest address. Okay. Let's say we have the value. This is a hex value, 78, 34, and 12. This is hex value. So what is the most significant byte here? This value, first of all, is 4 bytes, right? Especially when I write it this way in hex. This is 4 bytes. It's 1 byte. So what is the most significant byte here? 78. Yeah, 78 is the most significant byte. Okay. So on the platform we are using, on most of the platform we have, the convention is when we store those 4 bytes, we are going to store the 78, which is the most significant byte, highest address. Let's say this 4 bytes, we are going to save at the address 0. Then the least significant byte, which is 12, will be stored at address 0 because each address can only save 1 byte. Then 34 will be saved at address 1, 56 will save at address 2, and 78 will save at address 3. That's it. Some machines are using big endian, but we're not using those machines in this class. Okay. So we can skip that. The x86 32-bit, we have 8 basic general purpose registers. They are general purpose registers, which means they can be used for all kinds of computations. Their purpose is general. 1 flag register or extended flag register, 32-bit, called E flags. There is 1 instruction point register or counter register. That one points to what is the next instruction to be executed. Then there are many other special registers, but we do not need to cover most of them for the computing system class because we were talking about kernel. We talk about those special registers. In this class, we mainly hack at the application layer. The general purpose registers are EAX, EBX, ECX, EDX, ABCD. Then ESI, you can remember this as extended source index. ESI, EDI, extended destination index. Then ESP, stack pointer, very, very important for this class. EBP, extended base pointer, also very important for this class. So those are the general registers. Especially for EAX, EBX, ECX, EDX, you can also refer their lower bits. You can refer its lower 8 bits as AL, a little bit higher as AH, or the lower 16 bits together as AX. So this is for backward compatible with very old Intel CPUs. So when Intel released their early CPUs, it was only 16 bits, I believe. So they only have AX, BX, CX, DX. They do not have EAX. Then starting from 84, 86, I believe, or 83, 86, they become 32-bit of CPUs. The registers become 32-bit. That's why the name is changed to EAX. The modern CPUs, what you guys are using, we are using 64-bit of those registers. So they are not called EAX anymore. They are called RAX. We will say them later. So the E flag registers basically has many interesting flags, and each flag is just 1 bit. It shows that the previous computation, there was a carry, whether there was a borrow, the computation result is 0, whether the result is elective, something like that. So there are carry flag, parity flag, 0 flag, and sign flag. Pointer, the IP or EIP is a register, and this register in some other architectures also called program counter, PC. Then this register holds the address of the next instruction to be executed. Okay? So what do we mean by address here? What is the address? What do we mean? What's the context here? Address.
The memory address.
Exactly. The address here means the memory. So in the CPU itself, the registers, they do not have address. They have names, right? P holds the memory address of the next instruction to be executed. That's it. Then there are many other registers for this platform. Some of them were for multimedia computations. Some of them are just used by operating system. For example, we're showing those GDTR, IDTR, TR, those registers. They are mainly for the operating systems to use. So in this class, we do not really use them. We will use CS, SS, DS, ES, FS, GS a little bit. Some of the hacks we're going to use those registers. Those registers are accessible from application layer, usernet. There are also many debug registers, DR0 to DR15 for hardware debuggers. There are also some configuration registers, CR0 to CR15 configuration registers, CR. One of them is CR3 that stores the memory table's address. Instructions. In this class, we use the Intel syntax, and each instruction is in this form. There could be a label that's optional. Then there is a mnemonic. You can say that's the name of that instruction. Then you can have multiple arguments for that instruction. Or at this layer, we call it the operand. So the label is optional, and different instructions, they may have different arguments or operands. Some of them do not have any argument. Some of them can have up to 3. And the operand can be an immediately value, which is just a number. It can be a register. It can also be a memory address. Let's see some examples. First instruction we say here is HLT. It basically puts the CPU into sleep. Okay. So when the CPU executes this halt instruction, that CPU goes to sleep to save energy. So this instruction doesn't need any argument, just the HLT. The next instruction is INC, increment. It will increase the value of a register or memory location by 1. So it takes one argument, which is the name of the register or a memory location. The next instruction is addition. We add two numbers together. So we need two registers. So technically, after we add them together, we still need to save it somewhere, right? So we need three parameters. But in this case, the destination is the first register, is the first operand, and we add both of them together, and the value is stored in the first operand. That's why we only have two. Then we also have integer multiplication, IMUL. We can have three operands. So in entire syntax, the first operand is the destination. In AT&T syntax, the second one is the destination. This class, I prefer to use entire syntax because it will be easier for you later when you switch to any other platforms. If you are working on ARM, you work on RISC-V, you work on MIPS, they do not have two syntax. They do not have Intel or AT&T syntax. They only have one syntax. And they always put destination as the first operand. Okay. AT&T syntax, we actually use that in computing system class. Destination is the second one, and that confuses a lot of people. This part we can skip. Okay. So how do we address memories in this syntax? You guys probably still remember, in AT&T syntax, we use a pair of parentheses to do that, right? In entire syntax, actually, it will be a little bit easier to understand. We just use a bracket to represent memory location. Okay. So this instruction move bracket EAX EBX. So what is the destination here? Okay, that's about 50% correct. Yes. So the destination here, because of the bracket here, is actually the memory. Okay. So we're moving something from the register EBX to memory. How do we identify memory? We use the address to identify memory. And that address is stored in the register EAX. So basically, this instruction means we are copying 4 bytes of data from register EBX into the memory address specified in EAX. Okay. The instruction is called move. We're not really moving, we're copying, right? Because after you move in the register EBX, it still has the same value. It will not be reset to 0 or whatever. So this is basically copy. Next instruction, move EAX bracket ESI minus 4. Okay. So the source here is memory. We're going to move something from memory to the register. And the memory address is ESI's value minus 4. ESI is a register. And we're moving that to EX. There are a little bit more complicated syntax. Move CL. What is CL? CL is part of the register ECX. The lowest 8 bits of that called CL. So this is only 1 byte. Okay, we're moving 1 byte of data to where? To where ESI plus EAX times 1. Okay. So this is complex the syntax. So at the level, they can easily support array operations. When you look at this, right? This is an array operation. This is the base address of the array in the memory. This is the index in that array. This is the size for each item in that array, right? So at the instruction set level, we actually already support array operations. Go ahead.
Do you have to specify like move Q or move L? You just say
no. In AT&T syntax, you do. Here, you don't. There's another way to specify that. You still need to specify that. Yeah, I have an example later. Another example here. Moving something from memory to the register EBX, and the memory is at ESI plus EBX times 4. And we move to EDX. So this is basically what you asked. Sometimes some instructions can be a little bit ambiguous. Let's say the first instruction, move to memory address EBX, and we move the immediate value 2. Okay. This instruction can be ambiguous, right? Why this can be ambiguous? You don't really know the size of the number 2. You can use 1 byte to represent 2. You can also use 2 bytes, 4 bytes, 8 bytes to represent that. Just as the higher bytes are just the zeros, right? So you don't really know the size of that. But you are moving it. You need to know you are moving. If you want to move 1 byte, but the CPU mistakenly move 4 bytes, then the CPU will overwrite 3 bytes that it should not overwrite, right? That's why this instruction, this syntax here is ambiguous. That's why we need to specify how many bytes we want to move. In this case, the syntax, we have this byte pointer thing here to say, oh, we're moving 1 byte. Okay. So AT&T syntax, we will attach a B after that instruction. But when they compile to machine code, it will be the same thing. It's just the human readable syntax will be different. So if you want to move 2 bytes, then here is word pointer. If you want to move 4 bytes, so it will be double word, D word pointer. That's why I introduced you what is word and D word. So data, yeah. Each address can only hold 1 byte, yes. What if you want to move 4 bytes? So data movement instructions, we just copy data around. The most popular one is the move instruction. You can move from register to register. You can move from memory to register. You can move from register to memory, but you cannot move from memory to memory. There is no instruction to do that. Right? So look at those. Yeah, there's no instruction to do that. Because the hardware layer do not support that. Imagine if you want something from memory to memory, do not go through the CPU. Do you really need the CPU? There are actually other techniques like direct memory access, DMA, to do something similar to that. A very important instruction for this class is push. A lot of problems, a lot of vulnerabilities we see in this class is because of this instruction. This instruction will push some data onto the stack. For a 32-bit machine, the data is 4 bytes. For 64-bit machine, the data is 8 bytes. This instruction only takes 1 parameter. It can be a constant value. It can be a memory location. It can be a register name. Okay. If it's a register name, let's say push AX, it will push the value in EAX onto the stack. But where is the stack? This instruction does not specify where the stack is. Okay? It's not explicit in this instruction syntax where the stack is. Okay? The stack is wherever the register ESP points to. Okay? So even if it's not explicit in this instruction, you need to know that it always pushes to where the register ESP points to. And the stack goes from higher address to lower address. For our platform, it goes that. For other platforms, it can be reversed. It will first decrease the ESP register value by 4. Then place the operand at that new address. So ESP always points to what you just pushed. Okay. The reverse operation of push is pop. Pop instruction also only takes one argument. It can be a register, it can be a memory location. It will pop the top element of the stack into the register, let's say EDI. Then where is the stack? What is the top element of the stack? Where is that? Yeah, exactly. It is still what ESP points to. It's implicit here, not explicit. Another instruction is called load effective address. I want to emphasize this one because this one is a little bit confusing. Most people, when you look at this instruction, what do you think? Think about this instruction. Load effective address, EDI, bracket, EBX plus 4 times ESI. This instruction. You see something similar before. Move, right? Move instruction can also do this. Move EDI, bracket, EBX 4 times ESI. That will be a valid move instruction. But there are two different things. When you have move, you are going to move from this memory address, the value at that memory, to the EDI. Okay? You are actually reading from memory to CPU register. When you run this instruction, load effective address, you are not reading the value of from the memory. You are only getting the address of that. So here, basically, you are doing is EBX plus 4 times ECX, that value, that's the address, goes to EDI. So this one doesn't really touch the memory. That's why this instruction is a little bit confusing. This instruction doesn't touch the memory. So why do we have this instruction? This instruction, we want to do this. We need to do a multiply first, then we need to do an addition, right? That will be 2 instructions. So this instruction does 2 operations at once. So that's why also this is called the complex instruction set. I don't know if you heard of that before. So Intel CPU, we use the complex instruction set because the instructions, they are complicated. They can be divided into smaller, more simpler instructions. So most of our IoT devices, mobile devices, we use the RISC instruction. So RISC-V is the architecture. They do not have complicated instructions like this. They only have addition plus. If you want to achieve something like this, you cannot do this with one instruction. You have to do multiple instructions. So the arithmetic instructions, addition, you can add a number to a register. You can add a number to a memory location. The second instruction here, we are adding, we do not necessarily have the B there. We are adding 10 to the memory location where EAX points to. We can also subtract something from 2 registers, a number from a register. DEC is decrement, is just -1, or subtract 1. The reverse operation is INC, increment. We can multiply the content using the NEU instruction, and also we can shift the values, use SH, shift left, shift right. Okay. So obviously, the purpose is not to ask you to remember all the instructions. When you disassemble a program trying to find the bugs, you are going to say many unfamiliar instructions. But when you say that, you just need to Google to understand how they work, okay? So you don't need to memorize this. Control flow instructions. They are called control flow instructions because they will change the value in the register EIP, the program counter. Imagine you have many instructions. If none of them change the program counter, the CPU will execute the instructions one by one. Okay? Execute one, then the next one, the next one. But some of the instructions change the control flow. We do not execute the next instruction. We execute some instructions somewhere else. You do this in high-level programming languages as well. You have if statement, you have switch statement, you even have call statement. So by those statements, you are not executing the next statement, right? So here, similar thing. Jump. There are two forms. You can jump to a label. The label eventually becomes a fixed address. Okay. So when the CPU executes the jump to a fixed address, you basically will just execute that address. You can also have a register. Let's say jump EAX. So the first type we call it direct jump. The second type we call it. The second type is particularly interesting for security reasons. Think about that. The direct jump, the target is fixed in your code. If your code is not writable, if someone cannot tamper your code, then it will always jump to the fixed location. But the second one, you are jumping to a register, the value in a register. And the value in that register cannot be determined until you are about to execute this instruction, right? Technically, static analysis cannot determine the value there. And the attackers may find many ways to change the value so the attackers can execute other code. So indirect jump is very dangerous. So conditional jumps, they are actually easy to remember. They start with J, stand for jump, then there is a condition. JE, E stands for equal. Jump. JNE, jump when not equal. Okay, so JE is jump when equal, JNE is jump not equal, JZ is jump when the last result was 0, JG is jump when greater than, JEG jump when greater than or equal to. So let's say we have a compare instruction, compare EBX with EAX, then jump less or equal to another label. So what happens is the compare instruction internally subtract the value from EAX from EBX, but it will not write the value back to EBX. If we use a subtract instruction here, the value will back to EBX. We do not really write the value back. We only remember the value whether is greater than 0 or smaller than 0. Okay. So the next instruction will decide what to do based on the previous instruction's result. This one, jump less or equal. So if EBX is less than EAX or equal to EAX, we are going to take this jump. Otherwise, we do not take this jump. We execute the next instruction, which is not showing here. Yeah.
When you do that CMP command, is that just saving it for the next instruction, or does the next one get saved in a register?
It's actually saved in a register. It's saved in that E flag register. It's not saved back in the EBX or EAX register. If you do the subtract, it will save the value back to EBX and also E flag register. Yeah. And also, technically those are instructions, not really commands.
So if you do a CMP instruction and then a decrement instruction, you'll have lost.
Exactly.
Okay.
Yeah. So because you can only save the value of the last one. So this is the compare instruction. We'll skip this one. We already talked about. Okay. Another very important one, the call instruction. This is the same as in C programming, Java programming, you make a function call. Okay. So all those function calls eventually are compiled into this call instruction. The call instruction has two operations. To understand this and to easily remember this, we divide this into two operations. The first operation is push the current code location to the stack. Okay. Where is the stack again? ESP. Okay. So we're going to push the instruction after call instruction, that instruction's address, onto the stack. Okay. There is a stack somewhere else. It's not part of the code. The address of that stack is at ESP. instruction after the call instruction, the address will be pushed there. Then we will do an unconditional jump to the target of that call instruction, the operand of the call instruction. That's it. Those two simple operations. And the call instruction, the operand can be a label, which will be compiled into a fixed memory address. It can also be a register. Okay. If it's a register value, this is called an indirect call. Okay. And this obviously is also dangerous because at static compile time, you don't really know the value in that register. Only when you are about to execute this instruction, you will know where you are calling to. Okay. And before that, attackers may change the value. If this is a fixed value and your code is not writable, attackers will not be able to change that. Operation of call is called return. Okay. This instruction do not even need a operand. It can have, but most cases they do not even have an operand. And it does something very simple. It will pop a value from the stack, but it will pop it to a very particular register, which is the EIP register. Okay. How it works. We have call instruction. Let's say, I'm not sure if those guys can maybe let me write here. We have a call instruction. Call instruction, we have a fixed address, let's say 1FF. Okay. After call instruction, we will have let's say an add instruction, EAX, EBX, whatever. And this call instruction is at address, let's say 128. This instruction is at address 124. Assuming this one could be actually a little bit bigger, let's say 125. Those instructions, first of all, they are programs. They are stored on memory, right? So each of them will have an address. The call instruction is at the address 120. After the call instruction, there is an add instruction at the address 125. The call instruction is called 1FF. So when we execute 1FF, what happens? SP, this is a register, points to that stack. Okay. Will push the next instruction's address to the stack. What's the next instruction's address?
125.
125. So 125 will be pushed onto the stack. Okay. So after this, we actually go to 1FF. 1FF, we have many code. Okay. Eventually, because it's a call, this is supposed to be a function, right? The function eventually will return. So at the end, there is a return instruction. There may be many instructions before that, we don't care. The return instruction, what will this do? Will pop what ESP points to, right? So after you execute this return instruction, the EIP will have the value of what? 125. Which means we go back and start executing from here, right? So that's how we eventually implement call and return.
Then ESP changes.
That's a very good question. So actually, this piece of code, right? It may use the stack. It may have all kinds of pushes, but this piece of code of responsibility to make sure that when it returns, the ESP should point to the same place. According convention, it's their job to do that. Yeah. There are many ways to achieve that. It also involves EBP, which get very complicated. I'm not sure if we have time to talk about today, but next week for sure we will talk about that. Otherwise, you cannot hack this. Okay. So you see, This class, the very first hack we're going to do is to overwrite this address. So this call instruction is what we call a direct call instruction, right? Because the target is fixed. But this return instruction, technically, it's not a direct return. It's an indirect one. All return instructions are indirect ones because fixed. The target is somewhere in the memory. And if attacker has ability to overwrite this memory content, then when it returns, we're not going to return to here. We're going to return to some other place or our code, right? Our share code to do whatever we want. So that's basically the idea. So for the next several weeks, many of our attacks are basically revolved around this instruction, the return instruction. A little bit more about the runtime stack. This is the hardware support to support function calls. And also you need to pass argument parameters to functions. Stack obviously is also located in memory. The architecture we use, the stack goes towards lower memory from higher address to lower address. So when we push a value, we are adding something to the stack. However, ESP is decremented. When we pop a value, we are removing something from the stack, but ESP is incremented. There are some other stack instructions. We will skip them for today. One is enter. It's just equivalent to those three instructions. Also leave equivalent to those two instructions. We will talk about those three and those two instructions next week. Okay. They are very, very important. That's the 32-bit version of this machine. Then modern CPUs use 64-bit version. And many of your CPUs, Mac is probably on.
It is.
It's on?
Yeah.
Okay. Yeah, then the HP there, Dell, yeah, probably Intel 64. Yeah, ARM is also 64. Okay.
Yeah.
Then for 64-bit CPUs, the EAX is not big enough anymore. That's why we have RAX. So we do not only make those registers bigger, we also have new general purpose registers. Previously, we only have EAX, EBX, ECX, EBX. Now we have R8, R9, R10, tier to R15. Those are also new general registers. Okay? So not only they are bigger, there are also more. That's why the 64-bit machine are much faster. Then EBP also becomes RBP, ESI, RTI, RSP. Let's see another example. It's almost the same code before, we changed a little bit. But we are going to do 64-bit computation here. We are adding two 64-bit values together. When you add two 64-bit values together, how long is the result? If there's a carry, right? Yeah, actually 65 bits, right? So the most significant bit go to the flag register, the carry register. Okay. So in C, if you want to define a 64-bit variable, you use lang. So that's why we have two local variables A and B. Both are lang. They're 64-bit. Initialize to 0. We want to add them together. That's it. As a command line input, when you take as command line input, they are strings. So that's why we convert them into lang. Then we want to add them together. Of course, your input can be super long, so it can overflow. But this program doesn't consider that. Okay. We add them together. This function, the first parameter is the address. The first parameter is the address of the first argument. The second argument is just the value. Okay. but we are dereferencing the first one, so we are still adding those two values together. So what I want to show you is we will compile this into 32-bit and 64-bit. Then we compare how they are different. They're supposed to give us the same value, right? Let's say this is a 32-bit version of this. Use Intel architecture for this class. We are looking for the ln function. Okay, so here is the ln function. This is a 32 bits. We are adding two 64-bit values on a 32-bit machine, which means our register is not big enough to store that value. We actually store those values on stack. Okay? So ignore the first instruction, that's a security feature. Look at the second instruction here. We are moving ESP plus 4 to the register EAX. So the value we're using memory to pass in that value, and the value is at ESP, the register plus 4, that address. We're moving that to EAX. We're moving another value, also because of dereference here, we're moving that to EDX. Then we have two additions, right? One is addition, one is add with carry. Why do we have two additions? Because each addition can only do 32 bits, but we're adding 64 bits. So we add the lower 32 bit two values together, then we add the higher. So we have two values, both of them 64 bit. Two values, A and B. This is a higher 32 bit. This is lower 32 bit. This is higher 32, lower 32. So we first add those two parts, the lower 32 bit together, right? What is the output of this? How many bits? 3 bits. And where is that last bit? The highest bit is a carry. The carry is in the E flag register. Okay. So that's why when we do this, we're using the add instruction. Then we add those two parts together, and then we need to consider that carry. That's why we're using add with carry instruction, add C. Okay. So the first instruction is add, the second instruction is add C. Okay. So we're using, so this function has 5 instructions, consider return 6 instructions, consider the security feature 7 instructions. Remember that, 7 instructions, or the core part is actually 5 instructions. For 32-bit. Let's go to the 64-bit. The same program compiled using 64-bit on a 64-bit machine. Okay, so first, we are using just one instruction, add. Okay? Because this add can add 64-bit. We do have a dereference there, that's why we have 2 instructions. So we are saving 2 instructions here. Of course, it's a little bit more complicated than that, because the second parameter is directly in RSI, but we actually talk about this in computing system class, because when you guys program the function, the first challenge, you need to use this. But we will skip this today. Yeah. Later we'll talk about this. So this is a comparison of the same C code compiled into 32-bit and 64-bit. Let me give you a sense of what other architectures look like for your Mac. This is what the CPU looks like. So those are the general registers. There are many, many more general registers. 64 Intel has 16 general registers now, but for ARM, there are 31, 32 general registers. Each of them is 64-bit. And there are also many system registers at different execution levels. So this is Cortex-A for laptop, for phones, tablets, and also some servers. They also have different instructions. Then this is another architecture called Cortex-M. And this is for IoT devices, like those projectors. Your phones also have many co-processors. They are Cortex-M. In your cars, there may be hundreds of those kind of devices, Cortex-M. In your phone, there are multiple also. So those are quite low-end, very, very affordable CPUs. Some of those CPUs are just less than $1 each. Very affordable, okay? But there are many of those. So they have like how many general registers? Typically like 13 general registers. So those ones are stack pointers, registers, PC, basically the IP register in Intel, the status registers. So what other architectures look like? Okay, and then let's go to Linux file permissions. So for, because I want to talk about this because you need to understand how our hacking platform works, right? So Linux uses something called discretionary access control mechanism, which means each file has an owner. Owner has a discretionary rights to do whatever they want. This is an access control mechanism we use a lot in our physical work. Let's say your computer is yours. You decide you can borrow it to someone or whatever you want to do with it, right? So there is an owner. Then each file and the directory, they have an owner, have a group, then everyone else. Okay. So owner is basically a user that owns the file, owns this directory. Usually that's who created that file. Of course, you can also change the owner. Then there are groups. The groups can contain multiple users. All users belonging to that group, then they have the same access permission to that file. Then everyone else belongs to others. Then each file has 3 permission types: read, write, and execute. Okay, so this is not related to the memory management thing. This is in the file system. Okay. Read means you can use a tool to read the content of the file. Let's say we do a cat. You are reading the content of the file. Write means you can change the file. Execute means it is an executable. It's a program, you can run it. That's it. Then when you do a ls -l or -al, then you can see all the files in that directory or folder. Then you see an interface like this. Right? So what it means, there are multiple columns here. The very first column in this picture, this is on my very old laptop. The first one is either a dash or a D. Okay, dash here means this is a file, a regular file. D here means this is a directory. There actually could be something else. Then the next 9 columns. There are 9 columns. Okay, those are the permissions. Those 3 types of users are having on this file. There are 3 types of users: owner, group, and others, right? Then for each of them, they have 3 different permissions: read, write, execute. That's why we have 9 columns here, right? So the first 3 columns are the permissions for the owner. The middle three are the permissions for the group. The last three are the permissions for all other users. Let's just say one example. Say this file, bsdt.hex. I don't really know what that file is. So this column shows who is the owner of the file. Is myself. Group is also myself. So it means that I have the permission. My permission to this on this file is the first three column. In this case, it's R, W, and dash. R means I can read this file. W means I can write to this file. Dash means there's no X, means I cannot execute this file because it's not executable. Then for groups, we're not really specifying special groups here, so that doesn't really matter. It also has my name and only me there, so I will actually use this one. Then everyone else on this system, because this is a multi-user system, all users are sharing the system, right? For everyone else in the system, their permission for this file is readable, but not writable. There is no W here. There is no X, means they cannot execute this either. Okay, so that's a permission for that. Then there are directories. If you want to open that directory, you need the executable permission as well. Then we actually have an executable file. And we know that's a folder. About executable here. Go to the next instruction example. Then here is the link count. It's particularly useful for directories. It shows how many files are in that directory. So you implement a file system, so you know what link means. This is the owner. This is a group. This is a file size. This is the last modified time of the file, and also file name. Okay. This leads to set UID programs, which is how we developed our platform. Okay. And this is related to how a program is loaded by the operating system. On Linux or any Unix-like systems, including your Mac, each process, a process is a running program. Each process has 3 different UIDs, user IDs associated with it. The first one is called real UID. It is the user who created this process. When I type ls in the shell, I created the ls process. Right? When I do that, I am the real user, the UID of that ls process. There could be multiple ls processes, right? We have a server. Each of us is doing ls at the same time. There are many ls processes, but they are created by different users. So they have different real user field, UID. So the next one is called effective UID, EUID. So this is the UID the kernel use to evaluate the privileges of the running process. What the process can do, what permissions this process has, is determined by EUID. Okay. If it's a regular program, the EUID will be the same as RUID. The effective UID the same as real UID, which means it's a regular program. When you run this program, the effective ID is also whoever started this program. Then the OS will evaluate whoever started the program has a permission to do something. Okay. However, there is a special type of a program called set UID program. This is a Linux or Unix thing. Windows doesn't have this. Windows has for this. UID program is a special type of program. You need to specify that in the file system. This program is a set UID program first. When a set UID program is executed, EUID is not whoever launched it. ID is the owner of the program. Let's do this again. Let's say we have a server. On server, we have a program. Let's say we have a program cat. The program to read the content of a file. Right? Since this is a file on a file system, this one has an owner. For example, this owner is root. Then I log in the system. I'm the current user. My username is Zimi. When I type cat in the terminal, I'm trying to run the cat program, right? Then I'm zooming. So the real UID of that cat process and the effective UID of that process are both me, Zimi. Okay? I want to use this program cat to read a file. Let's say there's a file called flag. And this file's owner is root. And this file's permission is root can read it, cannot do anything. So I'm using cat. Cat process will have whatever permission I have. I do not have the permission to read the flag file, right? So when I run this cat program, it will not be able to read this file because it inherits what permission I have. Cat program is a set UID program. We can change this to a set UID program. There are many other programs already in the system that are set UID programs. A set UID program runs. The EUID is not whoever launches this. Instead, it's the owner. Okay? So if the CAN program is a set UID program, when it becomes to a process, its EUID is not Zimming, even though I am launching it, the EUID is root. Then it will be able to read the flag file because root has a permission to read the root file. Okay? So that is how actually our system is designed around this. There are many set UID programs in the system already, like SU, switch user, or some sensitive operations like mount something, unmount something. One of the homework today is for you to find all the set UID or set GID, group ID programs. They are basically the same. Because the group can also be the root group programs in the system. Here is another example. This is the program for you to read the very first flag in this class. And the program is very simple. Let me show you the platform first. Let's go to a real challenge. Let's use this one. So this is a challenge from last semester's final. And each challenge, there is a file called flag. See it? Flag. This file. Okay. Our goal is to extract the content in this flag file in each challenge. But you cannot just can it. So first of all, when you log in to the system, you are the user CTF. Okay? Every one of you, when you log in, you are the user CTF. If you do LSAL, you can see for this flag file, the owner is root. The group is also root here. And the permission here is, the first one is showing if this is a what? File or directory, right? So it's a file, so it's a dash. Here, the first three shows the permission of what? The owner. Who is the owner? Root is the owner. So only root has a permission to read this file. No one else has a permission. They don't have any permission. Okay? But now who you are CTF. You're not root. You can do a who am I command to say who you are. You do who am I, you get you are CTF. Okay? So you try to cat this flag. get a permission denied. You don't have a permission to read that.
I sue.
Hmm?
Do I sue the guy?
You cannot sudo here because you do not have the password for the root or whatever to do sudo. Yeah. So this is a terminal. This is a shell. When you type cat flag here, what you are doing is you are creating a new process of cat. And the cat is a regular program. Sudo is not, by the way. Right? So when you do that, the cat process will inherit your permission, okay, which is the other guy's permission. So when you use cat to read this, cat inherits your permission, so you do not have this permission to do that. However, for this program, for this challenge, we have a read. What's it? Challenge. This is the very first challenge for you to get the flag. We have a special program here. This program you can see here. The file itself, obviously. The permission is what? The root can read it, can write it, can also execute it. However, this is not X. This is S. Okay? S here means this is a set UID program. Others can read and run it. The group can read and write, and everyone else on the system can read the program and run this program. Okay? Which means everyone can run this program. And this is a set UID program. So when you, who are CTF, runs this program, what is the effective ID of this program? Because this is a set UID program, right? So when you run this program, even though your role is CTF, the effective UID of this process is root, and root can read this program, right? That's why when you do this, right? Sorry. You can read the flag. Okay? When I run this, my UID is still CTF. Okay? My username is CTF. My user ID is 1000. However, my EUID, effective UID, is root because this is set UID everywhere. Okay? And the permission, the kernel will evaluate the effective EUID, not the UID. For regular programs, they are the same. For set UID programs, they are not the same. And because of that, I'm able to read the flag. Okay. So all the challenges on our platform are designed this way. Let's say a buffer overflow or wrong. Would be fine. So all our challenges are designed this way. They are a set UID program, and they have bugs. And your job is to exploit that bug. You are trying to execute whatever you want to execute in this program. And because this program is a set UID program, by doing that, you will be able to extract the flag. Okay. Then let's take a look at the code of this read secret program. It's actually very simple. Only a main function. It will get who is the current user using get UID. It will also get who is the effective user, print them out, then just call the function print flag. The print flag is just to open that file and just print. That's it. Yeah. That's the source code of that. So there are many legit reasons why we have set UID programs, because a lot of programs, they need higher privilege, but they are not necessarily executed by the root. They should be executed by regular users. Okay? Even like you said, sudo or su, they are set UID programs. And this is a mechanism that only in Linux or Unix systems. Windows have a different solution. Windows doesn't have the concept of set UID programs. Instead, they use some concept like user account control. Basically, it's not a file system-based privilege escalation. A program runs. The program is not labeled as a set UID program or special program. It can be labeled as an administrative one actually. But when it runs, when it requests something, then there will be a dialog showing that if you allow this. So it's supposed to be an administrator to allow that operation. So that's a Windows way to do this. Okay, let's see. Still good on time. L files. Do you guys need a break? Maybe let's take 5 minutes. Take 5? Okay. We'll come back in 5 minutes. You don't need a VPN. We have a link.
Oh, perfect.
Yeah, so it's on the slides. So you go to my website,
Okay.
then you can find my slides. Lecture one.
I've already done that.
You already-
Yeah, I've already linked it. Yeah.
Okay.
But I was wondering when I'm home.
Oh, when at home, you have to VPN into full system network capacity. Yes.
Hi, you can go first if you want. Okay, I just wanted to ask, I don't know how much time I'll have after class, but you mentioned in the beginning that you were developing a new like platform for DTF. I would like to contribute basically,
Okay.
if
Yeah.
possible.
Send me an email.
So I just email you?
Yeah.
Perfect. I just email, do I need to send you like my resume or something? And I can send one, I
Yeah.
had one already.
Sure.
Perfect, thank you.
CCP actually is the command to do that. So the tool you usually use is GCC, right? Yeah. GCC actually has multiple tools. You can do a CCP. There's a command to do that. Yes. Oh, they're not here. That's basically the command. But not the necessary.
Oh, yeah.
Yes.
Your system works last semester. Pressure events. We did a lot of exercise. We did a lot.
I will show you guys the demo for all the challenges we do. We will show the demo. So, but it's not simply I can teach all the Linux commands. That's not the point of the class. Yeah.
Yeah.
Yes. Most of well, the important ones we will cover.
Yeah, I mean, I'm looking at the homework.
Yeah, we're
Right now, I mean, the homework is the same.
Is there like a piano system?
There is a piano system. Yeah, it's also on the slides.
Okay.
Yeah, the link is on the slide.
First, also like I believe
Yeah.
in some knowledge gaps in the class.
Yes.
So, what do you recommend?
The class is trying to be, like I said, self-contained. So if you follow everything in the class, you should be good. Okay. Yeah.
Yeah, that's another thing. Was applying from something else. Like I want to get that's my goal. But the first and happening.
Five five zero before the first yeah.
Okay. So next we will discuss the ELF file format. We do not need to go very deep, but you need to have a basic understanding what it is. So this is a standard file format for Linux, Unix systems for executables, object files, core dumps, which means if your program crash, there will be a dump. It will also use this format. And usually, or also libraries. So usually they have different extensions, but extension doesn't really mean much in the Linux or Unix environment. On Windows, the extension basically tells you what the file type is, but in Linux, Unix doesn't necessarily. Okay. But usually they use this kind of extension like .elf, .o, module, .ko. If it's a static library, SO or .a for static library, kernel module or other method could also be .mod. Also, if it's an embedded system, sometimes you could say extension like AFX, AXF, or even binary B, but they don't really mean that much. So this is a file format that contains the program, metadata, all kinds of data if needed. So it's kind of like the Windows .exe, right? So Windows.exe, that's called the PE file format, the portable executable format. Yeah. Linux uses ELF. So there are many tools we can use to manipulate ELF files. First is a file command. It's not only just for ELF files, it can for many different files. But file command basically uses the magic number at the beginning, magic code to identify the file type. So it will not be very accurate. If you manipulate the magic code, then it will be wrong. So let's say I have this ALS program on our system. I didn't program this. It comes with my Linux. If I do a file on it, it tells me what program it is. So this is an ELF file. This is 64-bit. It's use dynamic linked, which means it will use some library like C library. However, the C library is not compiled into this particular file. Instead, it's a shared C library with other programs. It will use this interpreter to load this program. The program is asking the OS to use this interpreter to load it. This is a hash value, and also it's stripped. Stripped here means the symbol information are not there anymore. When you compile a program, you use GCC, there are ways to keep those symbol information, like the variable names, function names, to help you debug. You can also strip them because CPU or the OS doesn't need those information to execute the program. Right? So this is a file command. Another tool I want to introduce is the readelf command. The readelf, you can analyze ELF files headers, tell you what informations are there. For example, we do a readelf -a, all the information of that. Let's just do that. Server to readelf a should have been LS here. It gives me a lot of information here. So all the headers of this ELF file. It first shows me the first 18 bytes of this file. There is a magic number, which is ELF 46. So 7F there is basically ASCII value of E. 45 is, no, 7F is, no, 45 is ASCII value of E. For C is ASCII value of L. For 6 is ASCII value of F. So the first 4 bytes are basically the magic number for ELF file. They should always be 7F then F. Okay. Then there are some version numbers. 64-bit. This is for a Unix system. This is dynamically linked. This is for the Intel or AMD CPU. x86 used to be Intel, but the 64 version is actually AMD. That's why you say AMD here. What is the version number? What is the entry point? And the entry point is very likely to be the underscore start function, actually, the address of that. And obviously, this one is the offset in the file. It's not the runtime address. Okay? Because eventually the file will be loaded into memory to run, and they have a memory address. But in the file, there is an offset in that file. Then this file has many headers. There is an interpret header. There is other headers. And they provide all kinds of information. Interpret, for example, defines the libraries should be used to load this ELF into memory. Load defines part of the file that should be loaded into the memory. There are many different sections. You should be familiar with those. Text section, that is where the code is, okay? Or where the code supposed to be. If you develop a malware, malicious code, or you use all kinds of packers, then you want to try to hide those information, then you will not put your code here. There is and the GOT, global offset table, and procedure linkage table. They have code and also addresses. We will talk about them later. There is .data section. Those are used for initialized global variables. When you program, you have global variable and they are initialized. They will go to the .data section. Okay? There will also be read-only data section. RO data. If you have a string, the string is hard-coded. The string is not supposed to change. So it should be read-only, not writable. So they can go to the read-only data section. Then for uninitialized global variables, they go to the BSS section. Okay? For C programs, the C standard actually requires all uninitialized global variables to be initialized to 0. C standard requires that. When you have a global variable, you didn't initialize that. C standard requires the compiler, the loader, eventually initialize that to 0. And those will go to BSS section. Okay? Because they will be initialized to 0, so in the BSS section, technically you don't need to have the initialized value. But for this one, the data section, you need to store the initialized value. Okay? So where is the local variables? You have been programmed, right? You have local variable, global variables, local variables. Okay, now the heap. Okay.
Start with the start. Are they on the start?
They are on the stack. Are they also in some of the sections? My question is whether they are in any of those sections.
Variable would be data.
Okay. Any other answers? Text. Okay. Any other? Okay. The correct answer is they are not in any of those sections because they are local variables. They are on the stack. They are technically created when you execute that function. They are created dynamically on the stack. It's also on the memory, but created dynamically. So they do not need to stay in the... Right? One function may have multiple local variables, and that function may be executed multiple times, or even a recursive function, right? So you do not really save that in the file. But local variables can also be initialized, right? Then do we need to save their initialized value? Because at runtime, we created them, we need to initialize it. But we still need to save those values, right? So some of the values can be hard-coded in the instruction, so in text, okay? Some of them could be in read-only data section, that's possible too. Okay. Many tools to manipulate ELF files. When you use GCC to compile a program eventually to executable, you are technically creating an ELF file. So GCC is a tool. Read ELF, I just show you. can read all the headers. Object dump, we already used that a little bit to show you the disassembly or reverse engineering L file, right? There are more advanced tools for reverse engineering, of course, we were using a little bit. NM is a tool to show you just the symbols. So we will use that also a little bit. Patch elf, if you want to change some part of the L file, you can do that. Object copy, if you want to extract some part of the file, L file work. So in the share code workshop, we're going to use those tools as well. Strip to remove the information. And of course, there are programming interface as well. There are libraries to do that. Memory map of a Linux process. For 32-bit machine, the address space is 32-bit, which is 4 GB of memory. A 64-bit machine, the address space is much bigger, but right now we are not using full 64-bit. It's too big, we are not using that. Modern system using 57 bits if they are using 5 levels of pager. Some systems are only using 48 bits. So virtual addresses, they are mapped into physical addresses by page tables. The smallest unit there is a page table, usually 4 kilobytes, 4 KB. Each process has their own illusion of 4 GB or 64-bit memory address space. But under the hood, your physical memory is limited. You don't have 64-bit of physical memory. And that is done by the operating system. Operating system provides that kind of illusion. So this is a typical memory map for a 32-bit Linux memory. In C, we define 0 pointers, right? For pointers, for addresses, 0 has a special meaning, which means this is not usable, okay? But imagine your physical memory. Of course, they start with 0, so it has a meaning. So the OS has changed the physical memory, virtualize that, have a virtual memory address. Then for the virtual memory address, the program use, even the OS use, we are not going to use 0, or even the first several pages, not just 0, even 1 or 2, we're not going to use it. So if you access them, you will say that's a null pointer, it doesn't exist. So that's why at the bottom of this virtual memory address, 0, we do not really map anything. It's not backed up by physical memory. Usually the text segment is at a relatively lower address. That's where code lives. The program actually lives here. The instructions lives here. Then we have the data segment, the data section. Initialize the global variables. Then we have BSS section, uninitialized global variables, and there will be filled with zeros. So how do you implement a loader for this? This is memory. You want to load the global variables from the file to the memory. Then you need to copy the data section here. For the BSS section, the uninitialized one, you don't need to copy because they all will be 0. Okay? Just need to know the size of it and do a memory set. Okay, much easier. After that, you have the heap, and the end of this BSS section usually is called a brick. Okay, that's why we have a system called brick or S brick. You guys took the computing system class. You implement the heap. You use the S brick system call this value. Then you get a heap. Right? Heap is a memory region you can allocate at runtime. Okay. So technically, stack is a region you allocated at compile time. How do you create a stack? You use push instruction, right? But the instruction is already generated here in the text section. So technically, the stack is created by compile time because you already created the push and pop instruction. But sometimes you need other memories at runtime. Imagine you develop a web server. You are getting a request from internet. You want to process that request. That request, the data was first get into your network adapter, then go to your kernel. Your kernel go to your application, your browser, let's say. Your browser want to process that. Then your browser need a that data. But the browser doesn't know the size of the data beforehand. It could be a request, it could be a small one, right? So that's why you need those kind of a dynamic memory allocator. Of course, the kernel itself also needs memory allocators. Anyway, that part is called a heap. And there are libraries. Usually we just use memory map to map those libraries. The higher address part, we have the stack. So the stack goes down, the heap goes up. Then usually the even higher address, we directly map the kernel memory. So even though the user space program cannot access the kernel, they are mapped there for faster context switch. That's OS stuff which we will not cover in this course. That's a map for a 32-bit machine. And how we implement the null pointer 0 in C and C++. We just defined in the older version 0. That's it. In the newer C++, we define as another keyword. But eventually, you still need the system support to achieve this, because physical memory technically have 0 address. It's not something special. Okay, so we're going to show the memory map of this program. This program doesn't do anything. This program will just get a character, the return. And if we do not include any character, then you will state it. So that's why we can see the map of it. Let's see which one is this. Process map. The 32-bit first. Okay. Background. Then I'm running that program. Then we can show its map. So we can see the map of this program. This is lower address, you can see. First of all, this is 32-bit machine. So that's why is 8 digits. All of them are hex. Relatively low, 56 something. And there are multiple modules of this, you can see. So this part you can see is readable, not writable, but executable. So basically this means this is the instruction part, right? This is the text part. You want to make bigger? This line, you can say this one is executable, which means this part is obviously the code part of that program. The other part probably be a data section, read-only data section, or SS section, right? Or something else. So here we have writable. So this is probably data section, because data section is your global variables. This should not only be readable, but also writable. Right? Then we have the heap. So here is a heap. It's readable and writable. Then we have the C libraries. So this is a libc. It's not part of this executable file. The kernel loaded that and mapped it to those addresses. Then we have the loader. We have stack. This is a stack. And we have other parts. So this part is somehow related to faster system code. I do not remember how it works. And I do not remember if this part is obsolete. But remember it's related to fast system code. none of the key part of today's class. So this is 32-bit version. Let's try 64-bit version. We run that first. We run that in the background. The ID is still 36. Six. So proc is a pseudo file system for us to get information on the system. So you can see here, first of all, the address is much longer. Previously, it's only this big, 8 digits. Now it's 16 because it's 64 bits. We still find executable section, probably the code, data, readable, writable section. We have the heap there, the C library, the loader, the stack, another base system call. This is another system thing to do faster system calls, base system calls. So that's a memory map. So there is a feature in modern system called address space layout randomization, which will randomize those addresses. So every time you run a program, the addresses would be different. So for the first half of the class, we disable that feature because we haven't teach you how to defeat that. Then for 2 weeks, we're going to enable that because your goal is to defeat that feature, the security feature. And the address space layout randomization we're talking about here are for applications. Okay? So every time one application is launched, those addresses will be randomized. The kernel also has a feature called kernel ASLR. And the kernel will also randomize its memory address, but it will only memorize when the kernel reboots. Imagine you have a server, you do not really reboot it very often, so that feature will not be that effective either. Yeah. Talk about this. Okay, system calls. So the operating system provides many system call interfaces for applications. Are basically ways for the applications to request services from the operating systems. So to make a system call, you do not use the call instruction. Previously, we talked about the call instruction. That is for function calls. You make a function call in one process, the same program. System call will make the CPU enter the kernel. And then the kernel will perform some services and eventually return to the program. So in some sense, a process where alternates between executing in the user space or kernel space. When it executes in the kernel space, it's actually the kernel code executing, but the kernel code may executing on behalf of the application because the application is requesting something. As an application developer, you do not necessarily directly make system calls. Even for C programmers, you do not necessarily do that. You make system calls through the C standard library, right? When you want to open a file, you call the C function open. Read something from the file, you call the C function read or fread. So those functions eventually they will make system calls. But you didn't program that part. The C library programmer programmed that part. But it doesn't mean you cannot do that. You can directly make system calls, and that is what we're going to do in this class. They have a C wrapper, has the same name. The system called open has a C wrapper called open. Okay. There are hundreds of system calls, and for Linux, Obviously, you can even add your own system calls. Something you should be familiar with: open, read, write, close, wait, execute, fork, or clone, exit, kill. Imagine how you develop your shellcode. Okay? You find a bug. That bug will lead you to execute arbitrary code. And your goal here, let's say the first goal is to just read the flag file. And what your shellcode supposed to do? You can inject arbitrary shellcode. And your goal is to print out that file content. Yeah. What you can do is, in the shellcode, you are going to do an open that file. Then you are going to read that file, right? Then you write that file to the terminal. Then you can get the content of that. You write, there are two system calls. There is actually another system call called send file, which is just one system call to read and write at the same time. If you want to create a shell instead of getting the content of a file, then you can do a exe CVE. Then do just a shell, like sh, right? So that's a more general shell. Linux has more than 300 system calls. Windows has 700 system calls. Like I said, usually you call save function. If you are a developer, you call the save function. There's a wrapper for that. There is a tool on Linux for you to see what kind of system calls a program has made. That is called S-trace. Let's say, let's start on this one. We do a S-trace ls. S-trace is a program, shows us what system calls ls makes when we run ls. When we run this, it will run ls, so eventually it will actually print out the file names in this directory, but it also shows us all the system calls this is making. Okay? Starting from exe CVE. Okay? First, we're going to type that. You are in a shell. The shell will create the new process ls. And that is through the exe CVE ls system call. Then after that, it will try to get where the data is, the break system call as break. Try to find some files, try to open some files. This open at is similar to open. It's just also have the paths. Find the status of some files. Try to load some library. So here we're trying to load a library. So we're using an memory map to load a library. After we load the library, we close it. We load another library. We read some files. Load many libraries. Say here. Let's say, or even change some memory regions permissions, sending some signals, doing a lot of crazy stuff, right? So here, let's say, eventually you're going to show us what files are there, right? Where is it? So here. When we do ls, it tells us what files are there, right? So this is the system call to show us on the terminal what files are there. It's just a write system call, and we're writing to the file descriptor 1, okay? So each process opens 3 files. They have the file descriptor 0, 1, and 2. 0 is std in, 1 is std out, 2 is std error. That's why we are typing our inputs through the terminal. We're looking at the output of the terminal. The output actually has 2 different, the standard output and also error output. But they all go to the same place, the terminal. So here, we are writing to the terminal to showing that raw gadget, challenges, those things. Okay. Then we are also showing more. Okay. So we actually have 3 write system calls to show us everything. So if we just do ls, you can say, that's what we're saying, right? This is the first line, second line, third line. And they are the LS program actually made 3 system calls to show that to us. So those are system calls. The first flag file, we actually skip the first flag because we use a secret flag thing. Let's see. We can skip this one. Some system calls you need to be familiar with. EXE, break. I don't think when we develop shellcode, we're going to use all of them. So let's just skip them. But if you are interested in what are those system calls, you can just check the manual or Google. You just do man2, then the system call name. 2 here is actually the system call entry in the manual. The Linux manual has different sections. Section 1 is for commands or functions. Section 2 is for system calls. We really make system calls in assembly. In the shellcode section, we will dive into this. Today, I just give you a brief idea of this. We use special instructions. Those are defined by the hardware and OS. The first instruction is the syscall instruction. Just the syscall. The name of the instruction is syscall. You can also do an int 80. The instruction here is int. The operand here is 80 in hex. So Linux uses the 80th hex 80th entry as the system call entry. I believe Windows use 21 in hex. So in Windows, it will be int 21 in hex. Or you can just use syscall instruction. There's also a sysenter instruction, but I think that's obsolete. So in this case, we mainly use int 80 or syscall, those 2 instructions. And this is the 32-bit version of the system calls. If you want to make system calls, let's say you want to make a fork system call. As a software application level developer, you just use called a save function fork. That's a save function. Save function eventually does this. Or as a hacker, you also need to do this directly. So what do? You set those registers values, then you run that instruction into 80. So fork, if you want to execute fork, you need to set the register EAX with the value 2. So that's a system call number. That's it. You don't need any other parameters. But if your system call is EXE, which is 11 in this case, so you want to execute a new program, you obviously need the path of that new program, at least, right? You also need arguments. You can put arguments there. You can also put environment variables there. That's why it takes up to 3 parameters. And so they goes to register EBX, ECX, and EDX. And you need to set the register EAX as 11 or B in hex. Let's say one example. To figure out, you can consider this as a very small piece of shellcode. You can also just consider this just assembly code. Shellcode is basically assembly code. Let's try to figure out what we are doing with this, okay? Several instructions there. Animation. Oh, I do have animation. Okay, the first instruction is XOR EAX EX. XOR is exclusive OR. So this instruction basically resets the register EAX to 0. Okay? So you can have different instructions to do the same thing. You can just move EAX 0. Well, that is, it will be actually longer because the 0 value is 4 bytes. And here, this instruction can only be, I think it's only 2 bytes. Okay? So this, then on the right-hand side, we have the stack. Okay, ESP points to someplace. That's where the state of the computer system right now. So when we execute XO EX gets 0, doesn't do anything. Then we do a push EAX. EAX has 4 bytes. which means we are pushing 4 bytes to the stack, and they are 0. Okay, the EAX there should be 0. Then we are pushing another 8 bytes. It's a little bit strange, right? We're pushing 8 bytes there. We don't really know what they are. Okay? So what do we get here? We are pushing something that's higher address, that's lower address. The EAX is actually 0. So what ends with 0? Here we have 4 0, but doesn't matter. Just 1 0 is enough. What ends with 0?
Non-terminated.
Terminated what? String, exactly, right? So this thing is probably a string. Okay? At the top, we have 0, that's high address. Low address, we have some value. We don't know what they are yet. Then the next instruction is the ESP, this register, points to this string. Okay? Then we move ESP, register EBX. Then we push EAX again. EAX is still 0. We have another 0 here. Then we push EBX again. EBX is the address of this string. The address of the string is pushed onto the stack. I think I don't have animation, just here. Okay. Then we move ESP to ECX. Then we move B to AL. Then we execute the instruction int 80. I already told you int 80 is a system call. Okay. Then what is AL? It's a system call number, right? For EAX, it's 0. Then we just move AL to B, which is a system call number. And that system call number is EXECVE. Okay? Then here we already know it's a string. The string is, let's say what the string is. The string, the lowest byte of this string is actually what? 2F, right? 2F, 62. Let's say, what is 2F? This is the ASCII table. What is 2F? Where's 2F? Here. F is forward slash 2F. Then what is the next one? 62. 62 is hex value 62. 2 is B. Hex value. Yeah, B. 69. Hex value I. Okay. Bin. Right. Then 6E. E is N. Right. Then we have another 2F. Okay. Then we have another 2F. 2 slashes. Then we have 73, which is S, then H. After this, we have 4 zeros. Okay, we don't really need 4 zeros. 1 is enough, right? Because we want a string. String ended with a 0. Okay, so here, we're missing 1. We have 1, 2. Oh no, we're not missing 1. Here. Okay, so that's 4. That's 4. Okay. So we are creating a new program, which is bin sh. Forward slashes. Does that 2 forward slashes really matter? In Linux, it doesn't really matter. Okay. In Linux, 1 slash is the same as many slashes. Let's say we do this. We can do bin sh. Right. We get the shell. We can do bin 2 slashes. It's the same. Okay. You can have as many other slashes as you want. they will be the same. Okay. So the slash here is just a padding, right? You do not want to put 0 there, that's why you put another slash there. Okay. That's just a padding. So this piece of code, that's why I call this piece of code a very simple share code, because it actually creates a share for you, and it returns a share for you. So it's a share code. But, this is probably 30 bytes, 20 something bytes. Okay. So in the share code workshop, your job is to change the share code to go to pass all kinds of constraints, like making the share code only 10 bytes, make the share code 8 bytes. You can only do certain operations in the share code. Yeah, those kinds of things. So we go to this one. This is basically how EXE CVE works. You have 3 parameters. The first one is the path of the program you are executing, and the path obviously is a string, so you need the address of that string, then the argument for it, and the environment variable for it. And since you just want to get the share, you don't want anything else. So the arguments and the environment variable just can be 0. The argument has to be this string and also end with a 0. So this is also the string itself. So that's why the assembly code was doing those things. The 64-bit version is similar. You can also use the instruction syscall to do that. The difference is, I don't know why, but 64 version and 64-bit, 32-bit version of Linux, the system call numbers are different. EXE CVE has a number 11 in 32-bit. In 64-bit, it has a number 59. Okay. I don't know why they changed it. If you want to learn more about how system programming works, this is a book I recommend to you, just Linux system programming. Also, let's talk about a little bit piping. Let's actually develop the shell so you know piping. So every process in Linux has 3 initial standard communication channels. Okay. It's called standard input, standard output, and standard error. Okay. So when you run an application, the OS already opens those 3 for your application. Okay. So the standard in has the file descriptor number 0. Standard out has a file descriptor 1. Standard error has a file descriptor 2. So when you open another file, it is guaranteed to have the lowest number of file descriptor available. So your program already OS open those 3 for you. Your program open another one, it's guaranteed to be 3. Okay. So OS guaranteed to do that. There are some command tricks you can use. Let's say the greater than symbol in the terminal means redirection. Let's say the echo high program. Let's try this. Go to top. So when we execute the program echo high, it will actually echo that back to standard out, which is a terminal. But we can redirect that to another file. Okay. Let's say when we do this, the output will not show on the terminal. Instead, it will go to the file 1.txt. So say when we do this, we do not say the high in the terminal, but it is in 1.txt. It's in that file. You can also do standard redirecting input by using the less than symbol. You can also pipe different programs together. So you glue them together. You echo a string, hello world. Without this part, hello world will output to the terminal. With this, the output will not go to the terminal. Instead, it will become the input of the next program. And the next program is word count. I'm trying to count how many words are there. Dash C here is means count word. So here we have 11 or 10 characters, so the manual will be 11 or 10. So by doing this, we glue programs together. Environment variables. Not only Linux, Windows also use environment variables. They are just a value pair. The format here is the name of the variable, equal sign, then the value of it. You can define this in a terminal, and when you create a program, this environment variables will be copied to the program on the program stack. We are going to use this in some of our hacking challenges to inject the shellcode, basically. So we can skip for now. I think this part is also not important for today, so let's skip it. There's one more thing I want to discuss before letting you guys go today. This one. Dynamic linking. Okay, like I said, when you compile a program, your program will use the C library. But you do not want to include that C library in your program. If you include that, then every program will have the same C library. Right? Then you are duplicating that in all the files. Then when you load them into memory, you are also duplicating them in the memory. Because they are the same. So the modern way to do that is there is only one version of that C library in the memory, and all the programs will share that. And this technique is called, it's also related to dynamic linking. It can reduce the binary size. We're going to see how the system does this. Airfile use some mechanisms called lazy binding to actually find out where those functions. Okay. So here you have your program. Your program is going to use a C library function or many C library functions. But those C library functions didn't compile or linked against your program. Okay? So when your program runs, the OS will load the library to the memory, but your program doesn't know the address of those functions because those functions are not part of your program. OS knows them. Right? Then, obviously, there is a step for your program to know where those functions are. Where is printf? Where is puts? Where are those functions? One way to do this is when your program is loaded, your program will find out all the C library functions, where they are, right? But this is a waste of time because your program will not use all of those C functions, okay? So that's why the technique here is called lazy binding, which means only when your program is making function calls to those library functions, your program or the loader will help to figure out where those functions are. The benefit of this is there are many C library functions. If your program doesn't use them, your program doesn't need to find where they are. So we do not waste time to find out where they are. We only find the programs, the functions we're going to use. So we're going to use GDB and also one example to show how it works. It uses multiple tables to do this. One table is called PRT, another one is called GOT, a global offset table, and the procedure. Procedure is basically function. Procedure linkage table. PRT some code sections, which means there are several instructions, not many. Then POT also has a POT subtable that is just the data. So let's say if you call puts or printf in C, then compile it into an L file, it doesn't actually know where put is. Instead, it compiles as puts at PRT. Okay, there is a table called PRT. That table is in your file. Your function call to puts were not calling the actual put function inside C library directly because you don't know where that is. Instead, you will call your stop, a small piece of code at the PRT section, and it has a name of puts. So that's why we call it puts at PRT. Then that puts at TRT will do something. It will first check if we already know the actual address of the put function. If it knows, we will call that. If we still do not know, then we are going to find out where that address is. Then we are going to call that. So this is how it works. You have your text section. Your text section at the C code level, you just call printf, which becomes puts, but it's not actually called puts. It's called puts at PRT. Then at runtime, goes to the PRT table, which has some instructions. This one, we're trying to find out if we know where that puts function is. If not, we're going to jump the default stop to try to resolve that function's address. Okay, then eventually go back here to execute. So we have an example to show this, where's my code? Let me show the code. Easy. Let's just do the 32-bit version. And we're going to use GDB to do this. I have code for this. Remember. Code. Oops. Okay, I don't have source code here, so I'm going to show you. This is the main function. The only place you need to pay attention is here. The source code, we make two function calls to printf. And after compilation, we get two function calls to add PRT instead of printf directly. We're going to debug this to show that those two times we are going to call into different addresses. The first time we are going to go through complicated resolution to get the actual address of puts. The second time we're going to directly call puts. Very quick. Right? Let's see. And at the same time, we can learn how to use GDB. So to run this program in GDB, you just need to do GDB. This. Then now the program is not really running. Set a breakpoint. We use the command B. We want to set a breakpoint as the main function. Now we set a breakpoint at main. But actually, we also want to set a breakpoint at those two call to puts, right? But anyway, we can use R to run the program. So now when we run the program, we will hit the first breakpoint. So now we're at the breakpoint. And here we can assemble those programs, the function, the current function is main. From there, you can see we have two places, this one and this one. We want to set a breakpoint. So we set a breakpoint main plus, what's that? 40. Okay, so what's the syntax? Let me use another syntax. Star this, so we set a breakpoint. The another one is 207. Okay. So we set two breakpoint here. We use the B command. Now we run this program again. We continue to keep executing the program. Now we hit the first breakpoint. We do a quick disassemble here to see. Right now we are about to execute this, right? Now we want to jump into this. So we do a SI. We do a SI means step in. We step in, now we inputs. We do a disassemble again. You can see right here. There is a security instruction, doesn't matter. There is a jump instruction. SI again. We are in 74. We do a SI again. We are in 40. Okay. So core process here, the core graph here is way from address 1 F5. We call to which one address? 1 F1 to 70, right? After that, somehow we go to 40. Okay, so this is the first time we call this puts function. This from 1 F5 to 70 to 40. If we continue, eventually we hit the second breakpoint, 207. Okay, 207 to do SI again. We get to 70 again. So we keep executing. So see, now instead we go to the C library function puts, which address is 01E. The difference? So that is what lazy binding is doing here. We call the function twice. The first time, our program doesn't really know where puts is. That's why it go to 70, then 40, 70, that's the stop. Okay? 40 is actually the function to the C library function to resolve the address of puts. It's not really the function address of puts. Okay? After we resolve it, we already know where puts is. So the second time we call puts, we go to 70, then we directly go to the puts function, which is at 01E, a different address. We didn't resolve that again. Okay? So that is how lazy binding works here. Okay, so that's what I want to show you. Everything else is not super important for today. So all those ones, the commands, I just list them on this slide. Later, we're going to discuss this. But when you, if you need to refer back to those slides, write them here. Yeah, perfect. That's what I have for today. There is homework. Go to my website, then you can find the homework link. Click this, you get the document. Our document, you need to put your answers here. Show me also screenshots. The homework today is very simple. You need to read the syllabus. There is a secret embedded in the syllabus. There is a flag there. You need to find it. Then you need to register an account on our platform. Cat, you need to run the first flag and also get the reading function. you need to list all the set UID or set GID programs on our server. Run that AND32.1, 64-bit of AND32.1, and also 64-bit. Yeah, that's it for today. Cool.
Thank you.
Thank you very much.
I hope you guys come back next week. Okay, see you.